Okay, welcome to this video on igneous rocks. As you can see here in the picture, we see a volcano with lava coming out of it, and at some point this lava will cool down to form one type of igneous rock. Now, this lava ultimately begins its life as magma, and to understand then how igneous rocks form, we have to understand a little something about how magma forms. Now, you might think that heat is the main mechanism for creating magma, and you wouldn't be wrong, but it's a little bit more complicated than that. So here's Earth, and recall from a previous lecture that in the middle of our planet, we have the inner core. And one of the characteristics of the inner core is that it generates a lot of heat. And it generates this heat through radioactive decay. So essentially the inner core is like a very big nuclear reactor at the center of our planet. The heat generated from this nuclear reactor diffuses out through the rest of the planet. So this is just the heat emanating from the inner core and diffusing out through the planet. And so you might think that if we were to look at a piece of rock, say right here, you would think, well, there's enough heat there for this solid rock to melt and become magma. The problem with this idea is that there's a lot of rock above that. And so this creates a zone of very high pressure. Okay, so P there is representing all the pressure that's bearing down on this rock here that wants to melt. Now, all this pressure has a significant effect on whether this rock can melt or not. And to understand why that is, let's understand a little bit something about the differences between solids and liquids. So here we have an example of a solid, and you can see that all the molecules or the atoms in this solid are packed closely together, and they're in this fixed structure. Now, if we were to add heat to this solid, to make it melt, it would turn into this liquid. Okay, so we heat up this solid and it becomes a liquid. Now, what you'll notice is that the liquid has a very different structure. The molecules are not in any fixed position. They're essentially far apart from each other. And as a result, they have a lot of room to move around. So this molecule can move around in all these different directions. So can this one. And of course, this is one of the characteristics of a liquid, is that it can take the shape of any container that you pour it in. Now, what you'll notice is that the solid takes up a relatively smaller volume than the liquid. So in both of these examples, it's the same amount of material, it's the same number of molecules, but the liquid, because it needs to move around, it takes up a relatively larger volume. And so for most substances, this transition from solid to liquid results in a volume expansion. Now, coming back to the rock here that's kind of close to the inner core, and it's heating up as a result of the heat generated from the inner core, it might want to turn into a liquid, but all this pressure that's bearing down on it prevents it from expanding. And so again, all this pressure is preventing this phase transition from solid to liquid, because it's the pressure of all the rock above it is essentially confining these molecules, and they can't expand and they can't move around like they want to form a liquid. So all this pressure is preventing the solid from turning into a liquid, despite all the heat that's in that area. Now there are areas on the planet where there's less pressure, and one of these areas is in mid-ocean ridge. So we'll talk about mid-ocean ridges in a later lecture, but for now, we can just understand as a mid-ocean ridge as an area where two tectonic plates are pulling away from each other. So we have this tectonic plate on the left, this one on the right, and you can see by these arrows that they're moving away from each other. And also I want to point out that each of these plates has both continental crust, so you can see this is part of the continent over here, you can see there's a tree, and then there's also oceanic crust. And remember that because oceanic crust is denser, it tends to ride lower, and as a result, that's where the water collects. So we have an ocean here that's forming where we have oceanic crust. Now, again, these plates are pulling away from each other, and as a result of this motion, there's a gap that is formed in between the two plates. And by the way, this area here is known as a mid-ocean ridge, which again we'll discuss in a later lecture. Now, because there's a gap as these two plates are pulling apart from each other, this is an area of low pressure. Okay, so low pressure. Because the pressure is decreased here, magma is able to form. Okay, so this is all magma that's forming underneath this area of low pressure. And as we'll see later, this magma can rise up through this gap and form new crust. Now this process is called pressure release melting. And so it's a very self-explanatory kind of name. The melting is happening because of the pressure that's released in the area beneath this gap between these two tectonic plates. Now, another situation that leads to the melting of crust and the formation of magma is in an area called a subduction zone. A subduction zone is an area where you have two tectonic plates colliding and one plate dives underneath the other. So in this situation, we have oceanic crust colliding with continental crust, and because the oceanic crust is heavier, it dives underneath the continental crust. Now, one of the characteristics of oceanic crust is that because it's been sitting underneath the ocean for a long, long time, the rock is very wet. And wet rock has a lower melting point than dry rock. Okay, so this rock here has a lower melting point due to the addition of water. So this means that wet rock doesn't need very high temperatures to melt when compared to dry rock. And because this is all relatively close to the surface, there's not as much pressure, and so this is a perfect situation for melting the oceanic crust and forming magma. So this is the oceanic crust melting and forming magma. Now, the final place that we're going to look at where magma is formed is in what's called a hotspot. We don't know exactly how this process happens, but somewhere in the mantle, there's a jet of magma that forms. So this is just a jet of magma that forms in the mantle, and this magma shoots up, punctures the crust, and moves up to the surface to form very large volcanoes. So this is known as a mantle jet, or you can also think of it as a magma jet. So it's just a jet of magma that just shoots up through here and results in very large volcanoes and very very large lava flows as well. Hawaii is a great example of volcanoes that form in a hotspot. So now that we've got an idea of how magma forms, let's take a look at the different types of rock that form by the cooling of magma. This is the same situation that we saw before where we have oceanic crust subducting underneath continental crust. And recall that because the oceanic crust is wet, it has a lower melting point, and as a result, magma forms. So here's that oceanic crust melting and forming magma. Now, because magma is hot and buoyant relative to the rocks around it, it begins to rise. So just think of this like a hot air balloon. If you heat up the air in a big balloon, that balloon will rise up because it's buoyant, it's less dense than the material around it. Same thing with the magma. It's hot, it's buoyant, it rises up. And some of that magma gets trapped within the crust. And this magma that gets trapped within the crust cools down eventually to form plutonic rock. Now, because this magma is cooling within the crust and it's surrounded by thick layers of rock, it cools down very slowly. And because it cools down very slowly, the crystals in the rock have a chance to grow. And as a result, plutonic rock is characterized by having very large crystals. And just to give you an idea of how long it takes for plutonic rock to cool down, it can take on the order of hundreds of thousands to millions of years to completely harden and turn into a solid. Now, some of that rock makes it all the way up through the crust and forms volcanoes. Okay, so here's that magma coming up, and some of that may get erupted out as ash, and some of that rock may get erupted out as lava flows. Now, this type of rock is known as volcanic rock. And because volcanic rock is erupted out onto the surface, it cools down very quickly. And as a result, the crystals don't have time to grow. And so this is a rock characterized by having small crystals. So two main types of igneous rock. We have plutonic rock, which cools within the crust and has large crystals because it cools very slowly. And then the second type of igneous rock is volcanic rock, which erupts out onto the surface, cools very quickly, and as a result has small crystals. So let's take a look at some examples of these types of rock. This is an example of a plutonic rock, and this is a rock that we call granite. And you can see just how large the crystals are here. So there's a crystal right there. There's another one. There's a big one right here. And again, these crystals have an opportunity to grow really big because the plutonic rock cools deep underground. Now, our mountain range, the Sierra Nevada here in California, is composed mostly of granite. So, for example, here's a picture of Yosemite Valley, and all the rock you see here is granite. Now, this is interesting because we know that plutonic rock cools deep within the surface, and so this means that at some point, all the rock we see in the Sierra Nevada was many miles beneath the surface, and so this rock had to be uplifted and then exposed by erosion. Now, the other type of igneous rock is, like we said, volcanic rock. And so we have here, you can see an example of a lava flow. And here's an example of a volcanic rock once it's cooled. And you can see that the crystals are much, much smaller than with the granite. In fact, you can't see them with the naked eye, and you would need a microscope to see the individual crystals. Okay, so I hope that was helpful. Thank you for your attention.